So in this new series of videos, we are going to solve the exercise problems from contemporary abstract algebra by Joseph Gallian. So let us look at the exercises from chapter 0. So here's the first one. For n equal to 5, 8, 12, 20 and 25, find all positive integers less than n and relatively prime to n. Okay. For the sake of brevity, let us call the set of such, let us name the set of such positive integers. Otherwise, we have to keep on writing the positive integers less than n and relatively prime to n is this, for this value of n, for that value of n. So, let Sn denote the set of all positive integers less than n and relatively prime to n, where n is any positive integer. It's not a standard notation, it is something we have devised only for this solution. Okay. So we have to find Sn for the given values of n. Okay. Although it's not a standard notation, but it is a standard notation for something else. So I better not take Sn. Let us take something else. Let us denote it by Rn. Rn also has a meaning. In number theory, it denotes the nth repunit number, but it's something very specific. But Sn denotes the symmetric group of degree n in group theory. So let us not use that. This is Rn is less frequent. So R5 will consist of all the positive integers less than 5 and relatively prime to 5. So they are these numbers 1, 2, 3 and 4. That is because 5 is a prime number, and we know from our knowledge in number theory that every positive integer less than 5 is relatively prime to 5. Okay. Then next R8. For 8 we have to avoid the even integers. So here the numbers are this, because 8 has only 2 as its prime divisor. So all these odd integers less than 8 are relatively prime to 8. Then next 12. For 12 we have to avoid both 2 and 3. So because we have to avoid 2, so we have to concentrate only on the odd integers, and that too we have to see which one of them will be removed because of 3. So 1 appears but 3 will not appear, 5 appears, okay, after that 7, 9 does not appear because of 3, but then we have 11. So this is R12. R20. For R20, since the prime divisors of 20 are 2 and 5, so those are the things we have to avoid. So again we have to concentrate on odd integers, but now we have to avoid the ones which are related to 5. So 1, now 3 comes, so 5 will not appear, 7, after that 9, there is no problem with 9, then 11, 13, 15. 15 is divisible by 5 and 5 also divides 20, so 15 is not an option. Then 17 and of course 19, because these are primes and they do not divide 20. And R25. For 25 we have to avoid multiples of 5. 1, 2, 3, 4. Okay, so 5 will not appear. 6, 7, 8, 9. 10 will not appear. Then 11, 12, 13, 14. 15 will not appear. Then 16, 17. Okay, 15. Then the next one is 20. So 17, 18, 19. So 20 will not appear. And then of course 25. So that means 20 will not appear. I am again writing 20. 21, 22, 23 and finally 24. If you are familiar with you should be familiar with Euler's phi function, which calculates the cardinalities of these sets. That is, phi of n denotes the number of integers. If n is a positive integer, phi of n denotes the number of integers, positive integers less than n and relatively prime to n. If n is greater than 1 and if n is 1, then phi of 1 is defined to be equal to 1. So you can verify whether we have the correct numbers. Phi of any prime number is p minus 1. So 5 minus 1 is 4, so this has 4 elements. Phi of 8 is 8 times 1 minus 1 divided by 2. You multiply the given number by an expression like this, where here you will have the prime factor of the given number. If it has more prime factors, more expressions like that will appear, 1 minus 1 over that prime factor. So this becomes 8 times 1 by 2, so this is 4. Yes, 1, 2, 3, 4. Our phi of 12, it has two prime factors, 2 and 3. So 12 times 1 minus 1 by 2 times 1 minus 1 by 3. So this is 12 times 1 by 2 times 2 by 3. 4. So 1, 2, 3, 4. Yes. What about phi of 20, let us calculate it here. 20 also has two prime factors, 2 and 5. So this gives us, we will have, let us calculate it mentally. Here we will have 1 by 2, that will that if you multiply that with 20, you will get 10. Okay, and here you will have 4 by 5. That 10 and 5 together, they will give us 2 multiplied by 4, that means this is 8. 1 2 3 4 5 6 7 8, yes. And finally phi of 25, the only prime factor of 25 is 5, so 1 minus 1 by 5. This formula that I am using comes from number theory. We will see it when we will study number theory. So this is 4 by 5, so that means this is 20. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20, yes. So these are the positive integers less than the given integer and relatively prime to it. Determine let me write it here because the numbers have been given in a factorized form. 2 to the power 4 times 3 square times 5 times 7 square and 2 times 3 cube times 7 times 11 and LCM of 2 cube times 3 square times 5 times 7 square and 2 times 3 cube. Also the second integers are the same. GCD of 2 to the power 4 times 3 square 5 times 7 square and 2 times 3 cube times 7 times 11. Okay, GCD by definition, the way it has been defined in this book, it is the greatest among all the common divisors. So it is literally defined as the greatest common divisor. So common divisors of these two integers, right, will be formed by these prime numbers, these prime factors that we have here, 2 3 5 7. Here we have 2 3 7 11, right, and the common divisor should be able to divide both of the numbers. Okay, so that means whatever prime factors the common divisor has must be common to both of the numbers, because then only it can divide both the numbers. So here among these primes 2 3 5 7, 2 3 7 11, 2 3 and 7 are common. 2 3 7. Okay, now it should be able to divide both the numbers. Now here what exponent should I choose for 7? If I choose 7, then this number divides the second integer. But if I choose 7 square, although that would divide the first one, it would not divide the second one, because here we have 7 only once. So the exponent that appears for 7 is 1. That is the highest possible exponent. What is the highest possible exponent for 3? The highest possible exponent is 2, because if I take 3 cube, then the resulting integer would not divide the first number. So this is 2. The highest possible exponent for 2 is 1, because here it appears only once. So this is the GCD. Okay. And LCM of 2 cube times 3 square times 5 times 7 square. I think that's why the integers have been written in this factorized form, in their canonical form. The author has saved us from the extra work of finding the factorizations. LCM, on the other hand, it is also literal. It is the least among all the common multiples, that is, numbers that will be divisible by both these integers. Okay, so unlike the previous one where we considered the intersection of the sets of prime factors of the given integer, and that intersection gives us the common primes, in this case we have to take the union. 2, 3, 5, 7, 2, 3, 7, 11. So that means 2, 3, 5, 7, 11. Do you realize why? That is because this should be a multiple of this as well as this. That means all the prime factors that are appearing in the first integer as well as in the second integer must be there, because it should be a multiple. And because of that, the exponent in this case that you will consider will also have to be, there we considered the smaller one among, do you realize what we did here? 2 is present here, 2 is also present here. Here the exponent of 2 is 4, here the exponent is 1. We considered the smaller among the 2, the minimum one. So here we have 1. 3 square and 3 cube, among these two we have chosen 3 square, because 2 is the smaller one. Between 7 square and 7 we have chosen 7. Here we have to choose the maximum. So between 2 cube and 2 we have to choose 2 cube, because if we don't do this, then this integer would not, it will be a multiple of this, but it will fail to be a multiple of this one, because it already has 2 cube. What about 3? We must take 3 cube. 5 appears here, 5 does not appear here. Among these two appearances, or the non-appearance actually there, this is the highest, because here you can consider 5 to the power 0, here we have 5 to the power 1, so we must have 5. Just like that, here 7, among 7 and 7 square we have to take 7 square, and here 11 is not there, here we have 11, so this is the LCM. Exercise 3. So these are appearing as some bulk exercises. In one of them, several different types of things are there which are of the same nature. For example, in the first exercise we are given some positive integers. For each one of them we have to find the number of integers, positive integers less than that integer and relatively prime to it. Now here we have modular arithmetic. Determine (51) mod 13, 342 mod 85, 62 modular 15, 10 modular 15. Then 82 times 73 modular 7, 51 plus 68 modulo 7, then 35 times 24 mod 11, and finally 47 plus 68 mod 11. 51 mod 13 is the remainder that we would obtain when we divide 51 by 13. That's what it means, and the same meaning is also there for the others. So with that meaning, it's just a matter of calculation, and I will just simply write the remainders, the answers. So the first one is 12. You figure out why it is 12. If you subtract 12 from 51, the resultant difference will be divisible by 13. Like that, (342 mod 85) is 2. Then 62 mod 15 is also 2. (10 mod 15 is 10 itself. In the calculation of a remainder like this, if you get a number that has to be divided by the modulus which is less than the modulus, then the number itself is the remainder, because you see 10 is the remainder when we divide 10 by 15. That is because 10 is equal to 0 times 15 plus 10. And what makes us conclude that 10 is the remainder? It's because 10 satisfies these inequalities. Because 10 is less than 15, so we can consider 10 as the remainder. And by the division algorithm, we know that once we have a quotient and a remainder, they are actually unique. So we have only one remainder when we perform such a division. So 10 mod 15 is 10, then 82 times 73 mod 7 is equal to 1. To calculate this one, there are two ways. Either you can multiply these two integers and then with the resulting product you can find the remainder in the usual manner, or you can do this also. you can calculate 82 mod 7. Okay, that will be slightly less work because 82 is smaller than this product. Find the remainder. You divide 73 by 7, there also you will get a remainder. You find that remainder, then you take the product of the two remainders, and then you find the remainder when you divide that product by 7. In that way also you can do. In fact, let us just see, since I calculated all these things in calculator, so I didn't really do anything. Let's just try to use the other method that I have just said right now. In this case, if we divide 82 by 7, what shall we get? 7 times 1 is 7, 12. 1 is 7. So that means we get 82 minus 77. So this is 5. So here the remainder is 5. And if we like that, if we do for 73, this one is easier. Here the remainder is 3. Now we multiply 3 and 5. So that means from these two calculations I can say 82 mod 7 is equal to 5 and 73 mod 7 is equal to 3. Now I multiply these two, I get 15. Then I calculate the remainder of 15 when I divide it by 7. So which is 2 times 7 plus 1, so that's why the remainder is 1. Yes, it is 1. So this one is correct. Just like that product, for this sum also you can calculate the individual remainders and then add them, and then once again find the remainder. And this turns out to be the next one, 51 plus 68 mod 7. This turns out to be equal to 0. This is divisible by 7. Next, 35 times 24 mod 11. This is 4. And finally 47 plus 68 modulo 11 is equal to 5. You please verify all these calculations whether they are correct or not. Then exercise 4. Find integers s and t such that one is equal to 7 times s plus 11 times t. Furthermore, show that s and t are not unique. We can write the solution at once. Or let's just proceed like how the exercise has been presented. First we find a set of values for S and T, and then we show that some other set is also there. Note that one is equal to 7 times S, 7 times 3 plus 2 times minus 11, 21. Okay. 7 times minus 3, it will be minus 3, and 11 times 2, then we will have 22 minus 21, that is equal to 1. So for this choice, S is minus 3 and T is 2. That is and T is 2. S and T are not unique because we can at the same time also have a solution like this. 7 times 8 plus 11 times minus 5. So 7 times 8 is 56, 11 times minus 5 is minus 55, so that will also give us 1. So that's why in this case we can, in place of minus 3 and 2, we can also choose 8 and minus 5. So S and T are not unique. Exercise 5. Show that, okay, so this is a proof type of exercise. If A and B are positive integers, then AB is equal to LCM of A and B times GCD of A and B. So if we have two positive integers and if we multiply them, then the product will be the same as this product if we multiply their LCM and GCD. So this solution is a sort of, in fact this is a result from number theory. So we are going to use the structure of GCD which is already there in the text. We know that the GCD of two positive integers can be expressed as a linear combination of them where the coefficients themselves are integers. We know that GCD of A and B is equal to SA plus TB for some integers S and T. We know one more thing, the LCM by its very definition is a multiple of both A and B. Also, LCM of A and B is a multiple of A, so there it will be equal to MA. At the same time, it is also a multiple of B, it will be equal to NB for some integers M and N. Now next what we do, we multiply both sides of this equation by LCM of A and B. So the left hand side will be LCM of A and B times GCD of A and B, and the right hand side, the first term will be LCM of A and B times SA. Plus LCM of A and B times TB. Okay, so we are going to work with the right hand side for some time. Now in place of LCM of A and B, here we can write NB in the first term. So we have NB, and with that we have SA plus, in the second term, in place of LCM of A and B, we are going to write MA TB. So you can see that in both the terms we have AB. So we can use the distributive law and write this